Namaskar and a very good evening to one and all from Institute of Climate Change Research, the Maharaja Sayaji Rao University of Baroda. I take the pleasure to welcome Dr. Tomo Kaurane and Dr. Jarno, the speakers for today. I will also acknowledge the presence of Professor V.D. Pathak, who is a very senior person in the field of applied mathematics. My co-host for the program, Professor Dhanesh Patel sir, also the director for Office of International Affairs at the Maharaja Sayaji Rao University of Baroda, and all the participants who are with us on 3 different platforms. The program is live on 2 Facebook pages, that is the Facebook page of Institute of Climate Change Research, as well as the main Facebook page of the Maharaja Sayaji Rao University of Baroda. We had restricted the participants on the Zoom platform because we would encourage more people on the Facebook pages. So I welcome all of you once again for this series of webinars which we have initiated. And like I was mentioning the other day, that climate change is one subject which has affected almost all the aspects of our lives. And mathematics is an integral part when we talk about climate change research. So today we have 2 eminent speakers, Dr. Tomo, who will be talking on modeling climate change with remote sensing of forests as a mathematical challenge, which is going to be a very, very interesting topic. And also Dr. Jarno, who will be talking on mitigating climate change by implementing REDD+ programs. So once again, welcome to both the eminent speakers. I will now request Professor Dhanesh Patel sir to introduce the first speaker for the day.
Okay, thank you, Sanskriti. Dear all, and most interestingly, my participants, it's my pleasure to introduce the first speaker, Dr. Tomo Kaurane. He is a managing director of Urbonet Oy Limited in Joensuu, southern part of Finland. He did his MS in computer science in '98 from University of Helsinki. Then he did PhD in applied mathematics in 2002 from Lappeenranta University of Technology, Lappeenranta in Finland. And he got his honorary doctorate degree in forestry from University of Eastern Finland, Joensuu, Finland. Also from University of Jyväskylä, he got PS in Designated Information Technology. Number one, he's a very, what I mean to say that professional in terms of the forestry, and he's a leading person in the field of research in the area. You will understand from his talk, but let me tell you, across the globe. Now you see his background. He's you see his background. He's a man of computer science. He's a man of computing. He's a man of applied mathematics. And if you see his research interests, he's also a man of statistical estimation. He's also a man of financial markets, epidemiology, and remote sensing and other things. So if you see combinedly, Professor Tomo Kaurane, he is having a combination to do mathematical model in forestry. That's the whole aspects. Looking to his working place, he was in ECMWF, means European Center for Medium Range Weather Forecast, from 88 to 92. He was also associate professor at Lappeenranta University of Technology from 2001 to 19. And then now he's completely devoting his whole time to Urbonet Industry Limited. And of course, I mean, He was a founder director. Please remember, once again I repeat, he is a founder director of Arbonet Limited from 2000. It was established in 94, and till today also he is a managing director. He has worked on many projects all over across the globe, more than 40 to 50 projects. I don't want to quote anything. And at the same time, he has many publications internationally, nationally, yes, in good reputed journals. He has also supervised more than 15 PhD students. He has supervised more than 60 master thesis students, and he is a reviewer of more than 20 PhD theses and 100 of master thesis information. Now, this is his whole background related to academics and professional. But at the same time, I would like to quote, he's a very good gentleman, very helpful to everyone. Southern East Asia, he has done many help to many students, even in Africa, Rwanda, East Africa, everything. He did a lot of help to other peoples, gave a lot of projects to other students to get remunerations, to get a PhD. Yes, so he's a good human being, I must say, at this junction. At the same time, he's also good applied mathematician, and at the same time, he is also running industry in a very nice way. Okay, and therefore, today he is going to talk on modeling climate change with remote sensing of forest as a mathematical challenge. Thank you very much, sir. Now the floor is yours, sir.
All right, thank you very much, Dinesh, for those very verbose and kind words. They also serve to remind me that I'm not that young anymore, because to accomplish all those things has taken decades, but that's how life goes, and happy it's been going this way. So I'm happy to see, by the way, quite many familiar names on the list of attendees, both from Finland, from India, and from Africa. So as you said, this is a global event, and I've enjoyed working together with Professor Danesh and MS University of Baroda for, I think, over a decade already on various projects, and this will be ongoing. So today I will try to present quite concrete and practical challenges that face us when we try to mitigate climate change with forests, and this is often done through the so-called REDD Plus, RED Plus program, which will be in more detail introduced by my colleague, the head of RED Plus activities at Arbonaut, Jarno Hämäläinen. But I will pick up a couple of technically challenging issues, especially related to satellite imagery and airborne laser scanning, which mathematicians might help to solve, and also hope to show at the same time that they are worth addressing, that our ability to quantify the impact we might have on climate with forests depends crucially on such issues. So let me start sharing my screen and my presentation, and we'll move on. Now I need to find my right screen. This is a bit tough. Let me see if this works. Can you see it, my first overhead? No, not yet. Is it there? So because sadly when I started sharing, I realized I couldn't see the window I wanted to share. This one, yeah, okay, maybe this will help. Share, here we go. Okay, very good. This looks right. Jarno happens to sit right next to me, so I can check on his screen whether we see it correctly. And then I try to now make it full screen. Okay, all right. Okay, here it goes. So I'll start by first introducing Arbonaut briefly. So Arbonaut, I founded it together with some colleagues in 1994, and we currently employ on average about 60 people, 45 people on a full-time basis and 15 on a kind of more temporary basis. And they represent very many different nationalities, including India. In fact, one of my newest recruit is an MSU alumni, Paritosh Vasava, who did his PhD at LUT. We are headquartered in Joensuu, which is very close to the Russian border in eastern Finland, and we've collaborated and keep collaborating with a lot of research organizations and universities in many countries, focusing on forestry and then using mathematics and software engineering, computer science to do that purpose. And here's a map of some of our recent projects. It's outdated. I can see the number of countries has increased, and it has a rather nice collection of countries in Southern Asia. So we've had some projects in India, although not as many as I would have liked to have. We've been working actively in 2 neighboring countries, in Pakistan and Nepal, and at the moment also active in Bhutan. So much of what I say has been focused now on your part of the world and how these difficulties we face with satellite imagery reflect on South Asian forests and their role in climate change. Much of the work presented here is based on a long project we've had in Nepal, where, for example, the following people played a major role. I think the 2 top rows are mostly Argonaut people, and then many other collaborators from World Wildlife Fund, Tribhuvan University, and others, ICIMOD as well. Especially, I want to pick up Basanta Kautam, our head of projects in South Asia, and he's also got a degree from Dehradun, from the Indian Institute of Forestry. This project we conducted started in 2011 and was completed around 2014. We keep on working in Nepal on a different aspect, but that showed us both the promise and the difficulties that come from trying to quantify the carbon captured in forests. And so this is something that I presume many of you will know, but maybe not the mathematicians, that it's been identified about 80% of the annual greenhouse gas emissions are due to deforestation and forest degradation. And so the REDD+ program aims to revert that and rather make forests act like a carbon sink by planting more forest, by helping forest grow, and by stopping deforestation and forest degradation. But in order to grant the appropriate and right financial rewards for this activity, we must have a way to measure and monitor the growth of forests and also deforestation. And this is where remote sensing of forests meets climate and where mathematics needs to come into play. Now, Argonaut's specialty is airborne laser scanning, or LiDAR, light detection and ranging, which means that you fly on top of forests at about 2-kilometer height and keep sending laser pulses down to the earth. The density of pulses is quite high these days, up to almost 1 million pulses per second. And that means that we can attain more than 1 pulse per square meter from the ground. As you can see from this principle, laser beam is basically a very precise clock. It tells, because of the constancy of the speed of light, how far down did the reflection come. And so it allows us to create a 3-dimensional profile of trees beneath the aircraft. In Nepal, because of the slightly mountainous nature of the country, flying with fixed-wing aircraft is not feasible. It would be feasible in Gujarat, so we were using a helicopter where you can see the pod to which the laser scanner is attached at the side of the helicopter. And here are 2 examples. First, a very, very dense forest, and then a rather sparse forest. They're both from Nepal, Kailagat, Kanchanpur district. And as you can see, a dense forest looks precisely that way. The tallest trees there being over 40 meters tall and with a lot of vegetation above ground. Whereas a degraded forest with encroachment is much sparser, and this fact can be used to quantify the amount of biomass and thereby the amount of carbon in the landscape. In Nepal, we tried a novel methodology that we call LAMP, or LiDAR-assisted multi-source program for quantifying carbon. And this was applied very close to India, in the Terai Arc landscape, which is the border area in Nepal facing Uttar Pradesh, essentially in India. And those red squares are 5,000 hectare blocks, so 5 by 10 kilometer blocks, which we flew by LiDAR and then hope to generalize the data gathered from those into the entire Terai Arc landscape, so the whole area denoted here. Altogether, those blocks, they represent about 5% of the Terai area, so we hope to achieve good estimates with just a 5% sampling density. And obviously, this is already where mathematics comes in. You have to do the sampling right so that it's a proper statistical or probabilistic sample that represents the forest accurately, yet it should also cover the most relevant forest types. And the area has relatively lot of forest, but it's still like a small percentage of the total area because of agriculture and mountains and so on. So the balance between representativeness of the sample and the probabilistic correctness of the sample is non-trivial. Then also LiDAR allows us to engage in other activities, tiger conservation, where Nepal has done a very good track record, and where India also has quite a big stake. And I want to mention this because my most recent collaboration in India has been around tiger conservation issues in the Pench Satpura tiger parks, so national parks in central India, where LiDAR was not used, but that's a kind of a global issue shared by the countries with tiger populations. And here's a depiction of all of those. Now, here you can see an illustration of how this LAMP method works. So there's a point cloud on top where which shows how the laser points or LiDAR points are reflected from different parts of the canopy. So you can see that quite many of them come from the top of the canopy and therefore represent well the top of the tallest trees. And a substantial part also falls to the ground and tells us where the ground is. The reason why, I'm going to go back 2 slides, why you see these forests here being on flat ground is that we have first removed the terrain, the shape of the ground from the pictures, so that whatever remains is basically due to vegetation alone and not shape of the terrain. So that's one of the advantages of the very good ground model, terrain model that comes from that. But in order to turn those LiDAR point clouds into forest parameters, we have to use field plots. So there has to be ground truthing. And there's an example of a crew making measurements of forest on the ground. And then forests are being described by certain parameters, which we try to estimate with covariates that are taken from the point cloud. And in the end, we hope to generalize the data so attained from the LiDAR covered areas into the entire Terai Arc landscape with a wall-to-wall biomass map. Here's the whole process. I'm not going to go into the details, but so you see it's like a 2-layer modeling exercise where first, or rather 3-layer, we first have the sample plots on the ground, which are measured on those places where we also fly LiDAR. And then we use those sample plots to build a LiDAR model for the forests, which we hope is representative for the entire target area. And then we actually sample from those LiDAR modeled areas what we call surrogate plots or virtual sample plots, which are relatively precise because LiDAR models tend to be, and hope with those abundant surrogate sample plots to calibrate satellite image-based models that would be then used for the rest of the country. And altogether, the result is a quite dense grid-based map of biomass captured in the entire area based on the kind of forest they have. And here's some of the results now then. How does it look like for the Thal region? So the histogram simply tells the darker the green, the more trees and the more biomass. The numbers are tons or cubic meters per hectare. So a dense forest may have over 500 cubic meters. In this case, we mostly have maximum 500 cubic meters per hectare. So everything is normalized to density of biomass, and then by a correcting factor that is turned into a density of carbon per hectare. Here comes some correlations. So this is the crucial mathematical part. These are real sample plots, quite big ones, and these calibrate the LiDAR model. And as you can see, the goodness of fit is over 0.91. So in this case, that shows that the LiDAR-based statistical model actually captures the field measured biomass on these 46 validation plots quite well. So the first stage of the modeling is reliable, that we can confidently say. But then comes the second stage, where we sample LiDAR and then correlate that with the satellite imagery. And there we already see that things don't look so smooth. Actually, it's a really hairy scatterogram. But if you look at it more closely, you see that it is unbiased, which is important. So when we try to measure carbon content forest per hectare, the most important property of the estimator must be that it doesn't introduce systematic error. And this shows in a diagonal shape of the scattergram, if you look at that. So the noise level of the scattergram is high, but the shape is broadly diagonal. It also shows, by the way, that if you try to fit a regression model, the regression line doesn't behave correctly. It doesn't hit the origin at the end. And that's one of the crucial things to keep in mind, that you shouldn't trust the regression line because it's qualitatively wrong. It tells that your zero height doesn't imply zero biomass density, although it should. But then we come to the problematic issues. So here was one of our results, the earlier ones, above ground biomass in 1999. Here comes, by the way, one of the important benefits of satellite imagery, that you can go backwards in time. And you can estimate the change of biomass over decades, because satellite imagery exists from past forests as well. And here you see, therefore, let me go back, the situation in 1999 and then in 2010, so 11 years later. I'll come back to the problems a little later. Here's a difference map. So that basically tells how biomass has changed. And as you can see, the more yellow and the more red, the more forest loss. So forest degradation, deforestation has taken place, and the more green, then there is further growth in the forest. So now we come to the challenges. The main challenge can be summarized by this first statement here. Nature is complicated and nowhere near normally distributed. So almost all our statistical models, they somehow assume that the variable to be estimated in some scale is normally distributed, but biomass is not, forests are not. There's significant systematic deviations in the distributions, and establishing precise empirical distribution is one of the main challenges mathematicians faced. And because we don't have this normality, it also means that estimating our uncertainty, so the precision of our estimates, is also very, very difficult. So now I'm going to briefly go through a number of cases where we find mathematical problems, and indeed just hope that you appreciate them. And if you have good ideas to suggest how to solve them, then here they go. Here you can see one of the examples. This is a zoom into the map, biomass difference map. And you can suddenly see that there is this shade gradient or shade step that goes through the estimate. On the right side, it's darker. On the left side, it's less dark. And this is visible also in the difference map. It should be obvious to anybody that this cannot be natural. Indeed, it isn't. This is simply caused by the fact that optical conditions in which neighboring satellite images, so-called tiles, are captured have to be, they are often different in quite minor way, like one taken in the morning, the other one in the afternoon, and they will not align. Their colors are different, the sun shines from a different angle, and that is brought into the estimation process, and we can't easily get rid of that. So a lot of attempts have been done into normalizing satellite imagery, but this is still the case today. Here you can see the same. There's like a dividing line in between the Terai forest map, where on one side systematically the lower afforestation, on the left side higher. Again, unlikely to be of real natural causes. Then here comes a particular property of satellite imagery. If you just were to use satellite imagery, they saturate. So as soon as the canopy of a forest closes, then satellite imagery no longer, it cannot tell whether trees are 40 meters tall or 15 meters tall. When the canopy is closed, it looks the same. And so for all optical satellite imagery, we get this kind of scattergrams, which level off at some maximum biomass, and they are not sensitive to the higher biomass amounts anymore. LiDAR is much better because it actually does see the height of the trees. So we get more realistic correlations, but it still doesn't mean the estimation is trivial, as you can see here. This is against real sample plots, which were measured in the field, 738 of those. And you can see that, especially with tall or high biomass values, the volatility, the variance is very high. When we increase the size of plots, then the correlation improves, because one of the things about forest that does follow statistics rather nicely, even normally distributed statistics, that if you average over larger areas, then the averages become more stable. So the forests tend to behave like a random spatial field, which has the same probability distribution, more or less uniform everywhere. So that means that if you average over a larger area, that means that your results will be more stable. They will have less detail, but the mean values will become more consistent. It doesn't still mean that they are correct, because there are systematic errors, but their variance definitely comes down. So small plots have high random variation and therefore high variance, but more small biological variability, whereas big plots have high biological variability, but small variance per unit area, because different parts of the plot average out each other. They will contain both big and small trees, whereas a small plot may just contain a few really big trees or none at all, and therefore the variability is higher. Still, many small plots may be enough to calibrate a model. And on the other hand, you can use a few big plots to validate a model to see if it behaves rightly. And this is what we did in Nepal. So I'll just go through a number of those results. So these were the same 46 validation plots with a 50-meter radius. And this is for the LAMP. No, sorry, validation LiDAR model on new plots. Okay, I'm gonna, yeah, here we go, the 15-meter case, and here we get the 30-meter case. So we had really large plots, and this is where these good statistics that I showed you earlier come from, that when we have almost 1 hectare plots, the results look very good. But if we keep taking larger plots, we'll have fewer of them because it takes a lot to measure, and eventually we lose the advantage by simply having too many samples to correct against. I will skip this technical detail. There is quite a lot of story about the size of plots and so on. I just put them here. Here's a good example of how the trees are located on these big plots. So you see that we had like a 15-meter and a 30-meter plot measured at the same time. So just simply measuring the distance of trees to the plot center and the size of trees. So that gives you an idea why the differences in estimates also depend on the plot size quite largely. And then here are some examples of what happens with increasing plot size. So with LiDAR, we can pretend that we have plots of different size. With LiDAR, we can calculate even a 100-hectare plot based on the LiDAR model and use the same exercise. And this is what you get with the smallest, like 1/4 of a hectare plots. Then we go to 1 hectare plots with a bit different sample. This is 10-hectare plot size, and this is 50-hectare plot size. So you can see that the variance keeps coming down. Estimates remain reasonably simple, but obviously the resolution is always, it doesn't show differences within this 50 hectares. So it will not really help in practice to have very many big plots, but it helps you validate that your model behaves correctly when scaled. And here finally 100-hectare plots. Let me see. Okay, then we tried to find different ways to correct for those systematic errors. And here we're using old forest mass that was provided by the government of Nepal. That is an improvement. But one of the challenges we face is this, that we should be able to tell at which period deforestation, forest degradation took place. And here the different colors, and also where we have regeneration, where we have deforestation and degradation and enhancement. And here you see the pattern looks right. So the activities around the edges of the forest, this is actually very close to the Indian border already. But whether we can trust that precisely those areas are the ones affected is still anybody's guess. Here is one interesting idea, just to finish off very soon here. We hope that we might be able to work in Uttar Pradesh, in UP, because that being a very populous state, as you know, has a rather small amount of coverage of forest, but some of the bigger plots of forest in UP reside right across the border from Nepal. And in the hope that they would be of similar type, so Sal or Shorea robusta dominated forests, we thought that we might be able to model the northern forest in UP by the same data sets. So we wouldn't necessarily have to fly LiDAR, because it's always takes money and time and a lot of bureaucratic decision. One of the challenges we face in India, by the way, is the fact that capturing LiDAR is heavily restricted legally. So it's hard to get point clouds and work with them when you're outside India. So, but satellite imagery doesn't have that restriction. So we're thinking that one way might be to look at the UP forest and see how they correlate with the corresponding Nepalese ones. And then here's another example of tropical forests, just to show. I mean, normally we think trees are like conical in shape, and northern trees tend to be, but tropical forests not so. They have these heavy buttresses, and this is another three-dimensional picture of a tree, like an X-ray into the center of that, computed from stereography, and shows that buttress trees, they often don't even have any stem at the bottom. They look very different from what our theoretical models assume. So yes, with this I wish to conclude my list of challenges. It's not exhaustive, there are many more, but I hope this gave you some idea about how do they look and what mathematicians could do to help in doing that. Thank you very much.
Thank you, sir. That was very insightful. Because we all know, those who are researchers in the field of climate change, they understand the importance of the change in the land use land cover, and especially the forest cover, which is responsible for the change in the meteorological parameters. I don't see any questions currently. Probably people will put their questions towards the end of the session. So maybe we can take questions for both the lectures together. So once again, thank you, sir. Thank you so much for accepting our invitation and giving this excellent talk for this webinar. I will request Dhanesh Patel, sir, to introduce the next speaker for the day. Sir, audio is on mute.
Thank you, Dr. Sanskriti, for allowing me to speak about Armo or Yarno. Once again, thank you very much, Dr. Tuomo, for giving a nice presentation. Before I start giving the introduction to Yarno, so Yarno Marcus Hamilanian is working in Arbonet Oil Limited as a manager. He did his MSc in forestry from University of Joensuu in Finland in 2001. He was also in Agricultural University of Norway from 98 to 99. He also did some kind of specialization in the area of geographical information system at Hemo Polytechnic in Finland. And he also did some kind of work in Ministry for Foreign Affairs of Finland. If you see his work kind of things, during 2000 to 2001, he worked as a research scientist at Faculty of Forestry, University of Finland, Eastern Finland rather now, in Joensuu, Finland. He was also worked as a forestry advisor in Stroh Enso Forest Consulting in Mozambique during 2002 to 2004. He also worked as a project leader in Senkort in Denmark. During 2006 to 2009, he worked as a head of Unit REDD Plus and Sustainable Forestry at Arbonet. And then he continued. He worked on many projects in Guyana, many even in Pakistan, in Tanzania with Finland, Uganda, and again for Finland, Senegal, Ghana, Kenya, Tanzania, Mexico, Denmark, and again in Mozambique. He has many publications and many reports. He has also done some book reviews. Yes, many conference proceedings and many international national conferences presented his talk. And he visited many countries, including Cambodia, Ethiopia, Ghana, Guyana, Kenya, Pakistan, Nepal, Bhutan, Rwanda, Senegal, Tanzania, Uganda. And he is also member of several professional organizations. He was in North Karelia Foresters Association as a board member. He's a board member at National Resource Management Projects in Tanzania, Society of Finnish Professional Foresters. And he's going to speak on mitigating climate change by implementing REDD plus programs. Sir, you're welcome, and your floor is yours now, please.
Thank you very much, sir, for this introduction. So I start sharing my presentation in a few minutes or seconds, rather. I believe that you are able to see the displayed screen at the moment. So anyway, I think that Tuomo gave many of the, let's say, technical insights, which I'm also crossing in my presentation. So, but anyway, the topic of my presentation is more, let's say, broad aspect of mitigating climate change by implementing REDD+ programs. And basically, the trees and vegetation in general plays a very important role in this scope, because they have ability to uptake carbon dioxide from the atmosphere. So they are able to basically all these carbon dioxide emission produced by the human activities or natural activities, the trees are able to sequestrate into their biomass growth and remove it from the atmosphere. So in this presentation, I'm mostly talking about the carbon dioxide emissions, which is also kind of exchange unit whenever talking about the emissions from the forest or land use sector. In general speaking, when we look at the international reporting and look at the different sectors, which are presented, how the emissions are accumulated from these sectors, we can see that that agriculture, forestry, and other land use, that sector represents 24% of the global annual emissions. Then, besides carbon dioxide, the forestry and land use sector in generally, there are also emissions, methane and nitrous oxide emissions emitted. And one of the key aspects whenever we talk about the REDD+ programs, I will explain later what REDD+, and Tuomo already referred to REDD+ earlier, but there are, let's say, 11% of all the global emissions are originating from the tropical deforestation and forest degradation. Just give an overview for you, what are the forest carbon pools or terrestrial carbon pools which are actually observed and monitored and accounted for their carbon stocks. So let's say above ground and below ground biomass, they are forming the living biomass pool. So this is the pool which is also very well visible, for example, when looking at, or let's say the above ground biomass is visible when we are looking at from the satellite perspectives. The below ground biomass refers to the root systems of a trees or vegetation in general. Then we have a second pool, which is the dead organic matter. So whenever the trees are, let's say, when they are, for example, harvested, there are some logging residues left in the forest, or they are, let's say, trees are destroyed by the natural hazards or some natural disturbances. For example, there's some generation of the dead organic matter, and this dead organic matter pool is consisted of litter and deadwood. And then the scope of climate change activities related to forestry, and whenever monitoring the impacts of these activities, also soil plays an important role in terms of sequestrating carbon. And normally, when we talk about the REDD+ monitoring schemes, then the focus is mostly on the layer of the top layer of up down to 30 centimeters of depth in the soil. So this just gives a kind of global overview where the above ground biomass and living biomass are generally concentrated on the globe. So the highest concentrations are found in the humid tropical zones, but as well in the subtropical zones. once when we compare, for example, to soil organic carbon densities, so those are more even, let's say, in the northern latitudes. Latitudes where it's found basically where the peatlands, for example, are there, or wetlands are found. So, but also like in case of Asia, for example, the mangrove ecosystems play an important role in many of the country programs when it comes to the climate change mitigation, through preventing deforestation and forest degradation. So this is more or less the, let's say, if quantifying the total amount of carbon in the forest ecosystems. So as said, the tropical and moist ecosystems are the most, let's say, concentrated with the terrestrial carbon. While then, when moving to the boreal or more northern ecosystems, forest ecosystems. So, for example, in boreal forest, there are a lot of peatlands, for example, where carbon is stored. So Paris Agreement, there's basically United Nations framework for climate change. So every year over the past years, there's a summit where climate change negotiators of different parties, country parties, they meet up. And there was an achievement 2015 to let's say, to aim keeping a global temperature rise of this century below 2 degrees Celsius compared to the pre-industrial levels. And now this Paris Agreement is let's say, becoming operational. So each of the countries, they have proposed so-called nationally determined contributions, where they give kind of they name the activities which will be implemented at the national level to be able to mitigate the climate change impact. So it includes activities from the agricultural sector, from energy sector, forest and land use sector as well. So, for example, in many countries, the tree plant is one of the activities which is promoted through this kind of commitments. So, idea is that every 5 years, there will be kind of assessment how this collective progress has been made through these national determined contributions, and then in order to achieve the overall target of keeping the global temperature at the agreed level. What we can say, there has been already the Kyoto Protocol in place in the past. However, now this Paris Agreement has a special role for land and forest sector, and it's well recognized in scope of implementing the climate change mitigation activities. And as Tuomo already referred to REDD+, what does it mean? That this word, it's abbreviation, REDD+ is abbreviation of reducing emissions from deforestation and forest degradation. And the plus sign here means that, and refers to not only just conserving the forests as such, but also being able to, let's say, manage forest better in a sustainable way, getting the benefits out of forest, and also maybe improving the carbon balance of the forest. And the REDD+ is not only about the trees or forests or carbon; it's also about the people. So, in the long term, while the local populations, for example, they contribute to reducing emissions from forests, they also may gain some livelihood impacts and positive impacts and income through these activities. But also keeping in mind that at the same time, while doing those conservation efforts, so biodiversity, and there are also some other, let's say, products and other, let's say, other forest products, for example, which can be then sold and produced, for example, instead of, let's say, harvesting trees or, let's say, clear cutting the trees. Then just giving an overview of the countries which are active in the REDD+ field. So many countries where it was displayed by Dr. Tuomo here, where we have been active at Argonaut, so it's quite nicely overlapping with these countries. So anyway, mostly the European countries which are highlighted for here, and also Australia, and USA, they are supporting strongly the REDD+ project implementation in the tropical and subtropical countries which are listed and displayed here. Mongolia is in fact the only boreal country, the boreal zone country, which is, let's say, active and has been supported by the donors in REDD+ implementation. So here we see the what's the conceptual difference between deforestation and forest degradation is that in deforestation the area is let's say suddenly converted into some other land use permanently, while the forest degradation is rather like a process, can be a slow process that there are some let's say tree species, for example, are converted into other, let's say, other tree species. In many countries, for example, exotic species, for example, are not, when we talk about the intact forest, they contain the indigenous species. However, if you plant some exotic species, it means that, okay, forest is getting degraded, and it may not be, in some cases, some countries even classified as a forest. Yeah. Then looking at the reasons, the drivers for forest deforestation. For example, this shows the some regional differences are observed. What are the major drivers of deforestation? So, for example, subtropical Asia has the agriculture as a dominant, as well as in other regions. In some continents, like in Africa, for example, the mining seems to be forming a higher proportion of causes for deforestation. So here we can see then some drivers for forest degradation, which have been, let's say, accounted for this period 2000-2010 already in the past. So there we see that the major cause for degradation is timber logging, and also some fuel wood extraction in most of the continents. And again, just to remind that forest conservation is about trying to keep the forest and carbon stock intact at the same level, so that there's no activities implemented in the forests actively, rather like it remains protected. While sustainable forestry is about being able to use the forest, and enhancement of carbon stocks means that, okay, if the forest was degraded initially, then it can be reverted back to and converted back to let's say more dense forests. In different countries, because the REDD+ programs, they are implemented and coordinated at national levels. So it depends of the country context how this operationally happens. So it can be that nationally there are some jurisdictional areas within the country where the government, for example, is establishing some project areas, some REDD+ project areas, and then basically is trying to implement, following the national REDD+ strategies, and the forest officers are participating, and government and also other stakeholders are participating in implementation. And then this kind of impacts or carbon impacts are monitored, and then it allows the country to exchange the credits, the carbon credits or REDD+ credits, which are generated through these projects. So other way of implementing the project is having the kind of subnational different project. They can be some private companies, for example, which establish the project areas, and it's like kind of management is outsourced, and this kind of forest emission mitigation activities outsourced for the third parties. But then you may have also at the same time the governmental programs, but also the like national programs, and as well, let's say projects, which by different parties. So they are different, and it's called nested approach. And from the individual projects, if the carbon credits can be traded directly, if the, let's say, the national framework, legislation and policy framework is allowing that. Okay, here this is probably the, let's say, the key concepts. What you find on this slide is basically with help of establishing. There are two key concepts. One is the reference period, another one is accounting period. So the reference period is the time period in the history or in the past, which is used as a kind of historical baseline. And that is serving as a baseline when trying to see how much of those interventions, how well those interventions for REDD+ are working. So one could assume, for example, that if there are no REDD+ activities at all, one could think that, okay, naturally in some countries which are very forested countries, one can assume that and maybe see the development, foresee the development, there are higher emissions in the future coming or potentially resulting there. However, if REDD+ projects are implemented, there are some sort of agreed compensation baseline with the donors, so kind of target level which needs to be achieved, but then or let's say the compensation is carried out using that baseline. But then when REDD+ activities are implemented and monitored, reported and verified, the country can have kind of emission monitored emissions and verified emissions, so that compensation takes place then. What the difference is, whatever is the difference between compensation baseline and MRV emissions. So countries tend to establish national forest monitoring systems and monitoring, reporting, and verification systems to monitor the effectiveness of REDD+ interventions and quantify emission reductions. So there are normally two components. One is the satellite land monitoring system component, as well as national forest inventory component. So this activity data, so-called activity data, which is needed for composing the reference emission levels, but as well as monitoring emission reductions. So it's in case of deforestation and forest degradation, for example, it can be measured using and mapped using satellite images. So these are, for example, some of the satellite image examples, how the process is evolving from 1990 to 2005. Then we need another, let's say, besides activity data, we need emission and removal factors, meaning that how much, if the forest land is converted to open grassland, for example, how much emissions is per unit area in average taking place. So how many tons of carbon is lost while forest is harvested and converted to grassland. And the same way, if the grassland is planted again and to be used as a forest land, so how much the forests grow basically per year and remove carbon dioxide from the atmosphere. And the same it works with let's say degradation case. It's all of the carbon stock level is getting reduced, and some of the carbon stock reduction is leading also to carbon emissions. And how, let's say, in emission factors, how they are produced through the measurements, field measurements, and normally the bigger trees there are in the field. So normally these kind of concircular plots are used. So soil samples are taken from the smaller area, and also the seedlings and coppices are measured in the smaller unit, let's say radius plot, while then the trees get bigger, the bigger plot size. So normally it's up to 18-20 meters total plot sizes are used for taking the forest inventory samples. And then in order to produce some, because every single, let's say, all the trees with the different sizes are measured within the plots. So then the next step is to model how much carbon each of the trees contains, and then accumulate information first at the plot level, how much is the total carbon stock at the plot level, but also then convert the plot level information into hectare level units. And once we have the activity data and, let's say, carbon densities for the forests and these emission factors, it allows calculating the areal extent of deforestation and forest degradation multiplied by these emission factors, emissions, CO2 equivalent ton per hectare. And that allows us to quantify the total emissions for the certain period of time. And one of the important aspects is this uncertainty. So there's always uncertainty when it comes to the for example, forest biomass measurements or let's say emission measurements in generally. So each of the activity data and emission factors, the uncertainties related to those processes are quantified, and then total emission confidence intervals, 95% confidence intervals for those emissions are, for example, calculated using either error propagation or Monte Carlo simulation methods. And as Tuomo already mentioned in the previous presentation, I mean that initially the unbiased, let's say, often the countries start with some existing data elements, for example. So the most emphasis at the beginning, when there are not too many resources available for measuring the forest and mapping the forest, so getting the unbiased estimates, that's the most important requirement. But then at the end, the more and more the time goes on, so the stepwise one can have more accurate and precise estimates, investing more in forest monitoring. So thank you very much for this invitation for the presentation, and if there are any questions, so we are happy to answer.
Thank you, sir. Thank you so much for that wonderful presentation. Let me just check if there are any questions. Rather than questions, there is just a request to share the presentations.
I'm sure both Jarno and I can do that.
So, since we have V.D. Pathak sir with us, sir, would you like to say something today? Sorry, this is an impromptu invitation, but Pathak sir? Okay. In that case, I will request Professor Dhanesh Patel sir to summarize the talk for the day. Sir, mute. Audio is on mute.
Thank you, Dr. Tuomo Kurane and Jarno Hämeenliinen for such a wonderful presentations regarding the activities of Arbonate. And as I said in my earlier talk, that this Arbonate is a leading company in the area of research in forestry all over the world. Now, Professor Tuomo Kurane has tried to explain that how many people in his country. Actually, there are 45 people and 15 from different countries. They are working there. Then he has explained the how the LiDAR-based system works in Nepal, Pakistan, even in Satpura, yeah, in Maharashtra. Then he tried to explain the LiDAR models. He tried to explain the LAMP models. And as he said that nature and there is no normally distributed, he is absolutely right. And he tried to explain with some kind of probabilistic distribution. That's what they are using right now, with some kind of R2 error statistical analysis and so on. And the major thing what he tried to explain is a small plots and big plots. And that's a very important thing what he tried to understand, he tried to explain. Now the question is, if you see the whole presentation, my all students and my all researchers will understand where is the mathematics. People will ask the questions, where is mathematics? But you see, I mean, it's a satellite data. You have a huge amount of data and huge amount of data how to extract and how to work on it. That kind of thing they have done, and therefore that's what he's trying to explain, Arno, that how data can be handled very carefully. That's the what Dr. Arno told, Dr. Tuomo told us, and very nice presentations. He tried to explain the perspective. I mean, what is a big challenge to develop a mathematical model for that kind of things? Of course, they are doing statistical approach. They may have certain kind of errors. That's what he tried to explain. Then Yarno tried to explain some CO2 emissions reductions. Yes, then he also talked about for Paris Agreement in 2015. And basically he focused more on REDD+, that is reducing emissions from deforestation and degradations in developing countries. And he also tried to explain carbon density modeling. And then he tried to find out using Monte Carlo techniques, what is error propagation. That's what he's trying to say, that 95% confidence interval. That's what they say. But as I know Urbanet very closely, that they have a 6 or 7 softwares they have developed themselves, and they are using those softwares, and they are developing software, and they are changing the whole things according to the requirement of what the society, or according to the requirement of the problem. That's what they are doing, the project. Yeah, that's what I would like to say. That's the whole summary. Okay, thank you, Samskruti. That's what my.
Thank you, Professor Dhanesh Patel, sir, for the nice summary of both the talks. So that will bring us to the end of this webinar for today. But before signing off, it is my moral responsibility to thank each and everyone who is involved in making this program a success. So first of all, I will thank both the speakers, Dr. Tuomo and Dr. Jarno, for accepting our invitation and joining us here today for this wonderful topic, because it is the need of the hour. And both of you have thrown good light on the subject. And I'm sure that the researchers, young researchers, will pick up threads from your presentation and will be using them in their research. So thank you once again for your wonderful talk. As I have been saying that climate change is actually a subject which affects almost all aspects of our life. And to both the speakers today, I am glad to share that our webinars actually are attended, especially on the Facebook pages, by people from all walks of life. So those who are interested in core research in the field of climate change, they are definitely attending the webinars. But besides that, we also have a couple of people from NGOs who try to understand what is the impact of climate change and what role they can play in mitigation, etc. So this would be a great help to them as well. And then we have people who are just interested in knowing what exactly is climate change and how they can pitch in as individuals. So we have always tried to see to it that we invite a variety of speakers on various subjects. But essentially, I would like to mention that any research, core research in the field of climate change would be incomplete without the involvement of mathematical concepts. So that is where actually this series of 4 webinars is very, very important for the researchers. And I have to acknowledge the rock solid support of our Honorable Vice Chancellor, Professor Parimal Vyas sir, in all the endeavors which we have taken up at the Institute of Climate Change Research, because it is in a very nascent stage, and that's why the support is very, very important over here today. Also, the constant motivation of Dr. K.M. Chudasama sir, the registrar at the Maharaja Sayaji Rao University of Baroda, and all the Senate and syndicate members who are not visible on the programs but are silent supporters always. And besides that, for managing the media and the technical aspects, I will acknowledge the role of the communication cell of the Maharaja Sayaji Rao University of Baroda. I have to thank Professor Dhanesh Patel sir for coordinating for the speakers for all the 4 webinars. So thank you, sir, for your involvement and efforts in all the webinars, and also the press and media for the coverage, and most importantly, the participants who actually have joined us today, and also those who will be watching these videos post the event, because the videos will remain on the Facebook pages of the Maharaja Sayaji Rao University of Baroda as well as the Institute of Climate Change Research, MSU. And many a times what happens is that it may not be practically possible for few people to join during the webinar, but they definitely go and visit the page at the convenience of their time. So a big thank you to all those who are motivating us for organizing such programs in many ways. Keep liking the page of ICCR, Institute of Climate Change Research, the Maharaja Sayaji Rao University of Baroda, and keep sharing details about that amongst other researchers, so that we increase the reach of our speakers across the globe. Thank you once again to everyone who is involved over here. And we have the next webinar on 5th September. So I will invite and request all the participants as well as the speakers for today to join us again on 5th for a very nice technical session scheduled again. Thank you.